Sometimes we're going to need to write an integer, a positive integer, as a sum of smaller positive integers, and sometimes non-negative integers. Sometimes we'll include 0. So let's look at the different ways to do that. Let's let capital N be the non-negative integers. So 0, 1, 2, 3, etc. And let's let capital P be the positive integers. So 1, 2, 3, etc. Let's call a non-negative solution, or really an NK solution, to the equation A1 plus A2, etc., up to AK equals N. So we're going to look for K non-negative integers that satisfy this equation. We'll call that a weak composition of N into K parts. So for example, we write at the weak compositions of 4 into 3 parts. We could write it as 4 plus 0 plus 0, 0 plus 4 plus 0, 0 plus 0 plus 4. Or we could use 3's, 1's, and 0's. 3 plus 1 plus 0, 3 plus 0 plus 1, 0 plus 3 plus 1, 1 plus 3 plus 0, 1 plus 0 plus 3, 0 plus 1 plus 3. 2 plus 2 plus 0, 2 plus 0 plus 2, 0 plus 2 plus 2, and I guess we could also write 4 as 2 plus 1 plus 1. So 2 plus 1 plus 1, 1 plus 2 plus 1, 1 plus 1 plus 2. All of these count differently. Even though they're the same numbers rearranged, they count differently. So we've got 9 times 1, 2, 3, 4, 5. So I guess there's 45 of these. Oh, I'm sorry. I'm not counting digits. Each row is 1. So we've got 3 times 5. There are 15 of these. Now there's a nice formula for the number of weak compositions of N into K parts. The number of weak compositions of N into K parts is K multi-choose N. Now the K and the N in this formula appear in places which might be the opposite of where you'd expect them, so we have to be very careful that we don't confuse them. So to prove this, observe that we can write a multiset on 1 through k as 1 to the a1, 2 to the a2, etc. up to k to the ak, where this means that we use letter I ai times. So we use letter I ai times. Now if the total number of letters we've chosen is n, then we have a1 plus a2 plus up to ak equal to n. So if we choose a total of n letters with repetition, then a1 plus a2, etc. up to ak equals n. Furthermore, any multiset can be arranged like this, where we record the multiplicities. So that means that an n-element multiset of 1 through k corresponds to a weak composition. Now 0 is allowed because maybe we don't have any 2's, so maybe a2 is 0. So some of these exponent letters can be 0. So weak composition of n into k parts. So for example, we had the weak compositions 4, 0, 0, 0, 4, 0, 0, 0, 4. These correspond to choosing 1 4 times, or 2 4 times, or 3 4 times. And we had things like 1 3 0, 3 0 1. That corresponds to choosing 1 once and 2 3 times, or 1 3 times and 3 once, etc. All right, now let's look at the same problem, but let's insist that the solutions be positive. So no zeros allowed in these multiplicities anymore. So let's call a positive integer solution is to really be a pk solution of a1 summed up to ak equals n. So we're looking for positive integer solutions a1 through ak. We call that a strong composition of n, or just a composition of n. into k parts. Now the number of compositions of n into k parts is n minus 1 choose k minus 1. So if I had reversed the roles of n and k to make n multi-choose k the answer to the last problem, then I would be getting k minus 1 choose n minus 1 to be the answer to this problem. So however we choose n and k, one of these formulas is going to come out convenient with the n on the top, and the other one's going to come out inconvenient with the k on the top. Alright, so why does this turn out to be n minus 1 choose k minus 1? Proof is we can make a composition of n into parts by placing n dots in a row and then we can make a composition by placing k minus 1 bars in the n minus 1 spaces between the dots. So for instance, if we place dots here, we've got, if we place bars here, we've got 1, 2, 3, 4, 5, 6, 7, 8. Then we're writing 2 plus 1 plus 3 plus 2 equals 8. And as long as we don't put 2 bars in the same space between 2 dots, then there's always going to be a positive number of dots between consecutive bars. So we'll never place 2 bars in the same space. So how many ways are there to do this? Well, we've got n minus 1 spaces between the n dots. And we're going to choose k minus 1 of them to put bars in. So there's n minus 1 choose k minus 1 ways to do this. Now in the example, we were breaking 4 into 3 parts. So if we break 4 into 3 positive parts, the weak compositions that we still want are these. These are the only ones that didn't have any zeros in them. And this corresponds to writing 4 dots and putting bars here, or here, or here to make 2, 1, 1, 1, 2, 1, 1, 1, 2. So we should have 4 minus 1 choose 3 minus 1 ways to do this, which is 3 choose 2, which is 3. So that checks out. The end.